Alright, this is block 6 from topic 3. Should be open in your workbook to page 88. Remember that you can pause the video whenever you need to catch up, but pay attention to the time. That way you are finishing the video before the bell rings. Okay, block 6. I'm going to look at question 1 on page 88. It says create a table, a graph, and an algebraic rule to represent the relationship of pond side lengths S to the amount of fencing F. Okay, so our problem, I wanted to read the directions before showing the problem. So looking at our problem here, we have a pond like we had yesterday, but now we're going to fence it instead of tile it. So notice now we don't have extra corners we have to deal with in the fencing. We're just using the exact perimeter for the fencing we will need for our pond. So we need to keep that in mind. So if I have a side length of, let me get my pen. If I have a side length of 1, that means a 1 by 1 square. How much is the amount of fencing I need? Basically, how many sides long is all my sides? So 1, 2, 3, 4. I'm going to need 4 pieces of fencing. If I had a 2 by 2, so this is a 2 by 2 square. The amount of fencing I would need, 1, 2, 3, 4, 5, 6, 7, 8. For a 3 by 3, 1, 2, 3, 1, 2, and 3. So the amount of fencing here, I would need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So for 3 by 3, I'm going to need 12. Then if I look at a 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, amount of fencing here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Okay, so I created my table. I need to graph it and create an algebraic rule. I'm going to graph it first to know if it's even proportional or not, to know what kind of equation I need to come up with. So I'm going to graph my solution off to the side, and there is my graph. You may need to pause the video for everybody to copy down their graph. Okay, looking at our graph, is this fencing instead of tile, is fencing proportional or non-proportional? Well, we can tell that it is going to be proportional because it's going through the origin and it's a straight line, so I know it's proportional. So I know my equation needs to be in the form y equals kx. I don't need a plus or minus because I'm starting at a 0. The origin. They want to call, this is typically my x column, typically my y column, but they want to call this column S and this one F. And I need to see what F equals. So I need since it is proportional, I'm going to find a constant rate of change, or a constant of proportionality, or a constant rate of change. It could be either one. So I see that each time it is increasing by 4 in this one is by 1, so it was constantly here, constantly here. The main important number is that the 4, it's constantly going up, so my constant of proportionality, k, would be 4. It'd be 4x, but in this case, x is representing s, so that would be my equation for this proportional relationship. So the tiles for the pond was non-proportional, but the fencing is turning out proportional. All right, let's continue answering some questions. We're going to go to problem 2. And to answer problem 2, we're looking at the 3 things that we just found for our fencing problem. And it says to study the table, graph, algebraic rule, and the algebraic rule for the fenced pond fencing scenario. Is the relationship between the side lengths and fencing needed proportional? Well, we just discussed that. In the graph, we noticed it was proportional because it had a straight line and went through the origin. In the table, it increased by a constant length. And if I brought this back to 0, this increased every time by 4, so I'm going to decrease by 4, and that brings it back to 0, so I'm at a 0, 0. So I'm at the origin, and it's a straight line because it increased by 4. So that table says it's proportional, and it's in the form of y equals kx. So my equation is also proportional. So all 3 of them said yes, it is proportional. Three ask, if you found a proportional relationship in question 2, which we did, identify the constant of proportionality using each of the representations. Explain how you found it in each case. Okay, so if I looked at my table and I want to look at the constant of proportionality, and again, I'm looking at my constant of proportionality. It has one because it's a proportional example. So I know I can look for a constant of proportionality. To look for a constant of proportionality, we've written to find k, our constant of proportionality, we do y over x. This column was pretending to be x. This one was pretending to be y. So we're doing f, my y, over s. So I need to write these as my quotients to take a look at them. And when I write them as quotients, I see that this turns out to be 4 over 1. Well, I'm going to take a look at the next one. I get 8 over 2, and I realize, that reduces to 4 over 1. The next one is 12 over 3, which reduces to 4 over 1. And then the last one's 16 over 4, which also reduces to 4 over 1. So it says to identify the constant of proportionality. So what is my constant? My k. Well, we found k. 4 over 1 reduces to just 4, so my constant of proportionality is 4 over 1, or we can just call it 4. And we found this because they all simplified to 4 over 1. B is asking in the graph to identify the constant of proportionality and how we knew it was proportional. Well, we always know how something is proportional from a graph. It has to answer 2 questions. so I'm going to flip back over here, whoops, and take a look at my graph. Looking at the graph, straight goes through the origin, so I know it's proportional. But the question also asked me, what is my constant of proportionality? And we know we can always find that in a graph by looking for this famous 1 right there. So where it's 1, what is it hitting on the y? It's hitting 4. So that is how I know my constant of proportionality. I know it's proportional because it's linear and passes through the origin. And the 0.14 can be used to determine that the constant of proportionality is 4. We found that as well from the graph. C says, in the algebraic rule, what was our algebraic rule? It was this right here, right? F equals 4s. In that rule, we need to know how we know it's proportional and what my constant of proportionality is just by looking at the algebraic rule. Well, just by looking at the rule, I know it is in the form of y equals kx. Nothing was added or subtracted to it, so that's good. And then whatever is in k spot is going to tell me what the constant of proportionality is. So what number is in k spot? It's a 4. So that would be my constant of proportionality, my coefficient there. The coefficient is 4, so that's my constant of proportionality. Alright, moving right along. This is not in your book. We're just going to tie everything together here. This was my graph from the tiles that I needed with the pond. And we saw yesterday that it was linear, but it was non-proportional because it did not go through the origin. It's because I had those extra corners to deal with on the tiles around my pond. Then today we looked at fencing for a pond. We saw that situation would be proportional because it's a straight line and went through the origin. If they asked me for a constant of proportionality, could I find a constant of proportionality from the tile problem? No, that would be a trick question. It's not proportional, so I can't tell you a constant of proportionality. I could tell you a rate of change. I could also tell you a rate of change from here, but we have a fancier word we can call it because we know this problem is proportional, so we could call it rate of change or constant of proportionality. Both, well, was it both of them? It was. Both of their rate of change was 4. They both increased by 4. So if they ask what the constant of proportionality is of this one, it would be 4. If they ask for the rate of change of this one, it would be 4 because it was increasing by 4 every time. Alright, so let's go to our next problem in our workbook. And it says to complete the statements to show what you have learned about proportional relationships. So I have a word bank here. And I want you to pause the video, read through these sentences, and try and fill in the blanks with words from your word bank. Play the video again when you're ready to check your answers. All right, let's check our answers. It says the graph of the proportional relationship is a blank that passes through the blank. Okay, graph of a proportional relationship we know has to be a line that passes through the origin. Then it says the constant of proportionality is the blank. Constant of proportionality is the rate of change. Those are synonyms of each other. You can find the blank by comparing the blank between pairs of values in the graph or in the table. You can find the rate of change by comparing the ratios are just fractions, between pairs of values in the graph or in the table. In the graph, in the graph of a proportional relationship, the y value of the point 1y also tells you the blank and the blank. It tells you the rate of change and the constant of proportionality. Anywhere when you see that famous 1, whatever number is written there is your rate of change and or your constant of proportionality. Alright, I'm going to go ahead and do problems 5 and 6 with you, so you won't have these for homework, because they're a little challenging, make you think outside the box a little bit. So let's go to problem 5. It says, consider the image created with the 4 circles. Wants us to write an expression that describes the total number of intersections in the image. So intersections is where a circle runs into another circle. Or if I had a line, the intersection's right here. It's where they cross. Okay, so I need to write an expression for the total number of intersections in the image. Okay, well, I notice it's crossing here, 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 and here. I need to write an expression like we kind of did with the tiles yesterday. There's all sorts of expressions we can see. You might come up with others that I'm not even noticing right now. But one expression I see is I could write the top intersections. There's 3 of them. And then my bottom section, there's 3 of those. So there's an expression. Or I could see there's 2 right there on the first circles, 2 in the middle, and then 2 on the last one. So there's another set of expressions. Let me see if I see any more. I guess I could get crazy with it and go, there's 4 corner ones, then 2 in the middle maybe. And that gives me my grand total of 6 intersections. I don't know. That's good enough. Alright, let's move to B. It says, now write an expression that describes the total number of intersections there would be if the pattern continued for 7 circles. Draw out the pattern to see if your expression is correct. So they want me to write an expression for 7 circles and how many intersections it would have. This had 4 circles, and there was a total of 6 intersections. I'm just guessing here, but I see that 4 circles, you have 3 intersections, so it's kind of subtracted 1. And then you have the 3 on the bottom, 3 on the top. So if I go with that same scenario, I could do 7 minus 1 would give me 6. So I might have 6 on the top plus the 6 on the bottom. So I'm going to draw out my circles and see if I actually have 12. So 1, 2, 3, 4, 5, 6, 7 circles. And get this different color. Let's see, 1, 2, 3, 4, 5, 6. Ooh, I was right in my guessing. Then 6 on the bottom. So this expression could work out in my favor. Pretty good guesser. C wants us to write a general expression for the total number of intersections in a pattern with n circles. So they created a variable. So n is standing for my number of circles. And I have to write an algebraic rule. So I had noticed that we were subtracting 1 from my start number, and this n is telling me my start number. So I know n is having to take away 1, and then we always have 2 sets of that number. So whatever this is, we always have 2 sets of it. So I'm going to multiply that times 2. That should work out in my favor. Alright, so let's take a look at number 6. Doing the same type thing. It says consider the pattern in the first 3 stages of this tile model. So in stage 1, looks like I have 1 square. Stage 2, 4 tiles. Stage 3, I got 9. So A says write an expression for the number of tiles that will be in stage 4. So again, we're writing some sort of expression. Well, stage 4, I noticed it's 1 wide, 2 wide, 3 wide, so this one's gonna have to be 4 wide by 4 long. So if I filled in all my tiles here, that's what stage 4 would look like. So I could write a ton of different expressions mimicking this. I could do a 4 plus a 4 plus 4 plus 4. I could do maybe an 8 plus 8. The paper got fancy with it, and they noticed that this was stage 1, this was stage 2, this was stage 3. So they noticed on their expression, they said, well, stage 1, there was 1. Then stage 2 added 3. Stage 3 added 5 more. So they said, they looked and saw that stage 4 added 7 more. So that's how they came up with their fancy expression. There's all sorts of them I could create. So B says, is the number of tiles in a stage proportional to the stage number? Why or why not? I would have to look at this in a table to be able to determine that. I would say, if I'm looking at 1, has 1 tile, 2 has 4, 3 has 9, 4 we found out has 16. So I'm looking, and this is increasing by 3. That is increasing by 5. that is increasing by 7. So, it's not increasing by the same amount. So does that mean it's going to make a straight line? It means it will not make a straight line. So I don't even know what's happening in that 0, but I know this would not make a straight line. So could this be an example of a proportional stage? No. And our explanation could be this table. We could say no, not a straight line. All right. If you have some time left, you can get on a device and work on some online work. Remember that it cuts off tonight at 11:30, and the paperwork needs to be turned in tomorrow. If you have it done, you can go ahead and staple it and turn it in. And thanks for listening. Like, subscribe, and hit that notification bell. Peace out, home dogs.